Welcome to section 11.4 of the notes. This time we're talking about another way of taking the product of two vectors. It's called the cross product, and it only can be used in 3 dimensions, so in space, not in 2D, not in the plane. Some of the objectives are that we're going to learn how to calculate the cross product, and we're going to see what the property. One is to find the torque of a force, so it's sometimes called the moment of force, and another one is to find volumes in 3Ds of parallelepipeds. So the cross product is defined like this. If U is U1, U2, U3, and V is V1, V2, V3, then this is what the cross product looks like. First thing we need to really notice here, besides what the components are, but we'll talk about that later, is that the cross product of two vectors yields a vector. So when we talked about the dot product, we saw that what came out of the dot product was a scalar, a number. This time the cross product yields a vector. Now how do we get to see these components u2v3 minus u3v2, u1v3 minus u3v1, and u1v2 minus u2v1 with a negative sign for the second one? Let me just show you with a little animation. So here we have the vectors, and what you're going to do, it's quite convenient to write them vertically, it really helps, and then it's u2v3 minus u3v2 for the first component, so this is u2v3 minus u3v2 times I, and then the second component, the one in J, is u1v3 minus u3v1, but be careful, this one has a negative sign in front. And then the last one is u1v2 minus u2v1, and this time it's plus, so plus, minus, plus. These are determinants. You may recognize this kind of thing we do when we take the determinant of a 2x2 matrix, and if you remember determinants of 3x3 matrices, you always also had this plus, minus, plus that you had to be careful of. So this is a similar process, and we'll tie it more tightly when we do linear algebra later this year. Back to the notes. Now we're going to try to practice that. So if U is given here and V is given there, then U cross V is going to be 3 times 3 minus negative 1 times negative 2, so minus 2, which yields 7. And for the other two components, remember we'll change the sign, so let's just do 2 times 3 equals 6 minus negative 1 times 4, so plus 4. And with a negative sign in front, it yields negative 10. And finally, for the last component of the cross product, we'll have 2 times negative 2 minus 3 times 4, so negative 16. If we calculate V cross U with the same technique, we notice something interesting. Here's the solution, negative 7i plus 10j plus 16k, and that is that V cross U is actually negative U cross V. It's the same components but flipped. Finally, U cross U, if you proceed to doing the calculation, you'll see quite easily why this happens. The answer is 0. So U cross U equals 0, 0, 0. It's pretty obvious when you actually go through the calculations. So the cross product has some properties. Some of them we just saw above, and some can be proven using just some literal algebra, but even though we did it that year, it's all here, we are not going to do it now because it's a little bit tedious. If you're interested, you can look at this more carefully, but it's really standard basic algebra using letters with the definition of the cross product. One key one here is U cross V equals negative V cross U. We just saw examples A and B that illustrated that. If you do U cross 0, it's going to be the same as 0 cross u because of property 1, and that is going to be equal to the vector 0. Quite clear as well if you just try with an example. U cross u is 0, we saw an example above. And finally, what we will be calling the triple scalar product later on has also a property that u dot v cross w is the same as u cross v dot w. And you can pretty much mix it up any way you want, as long as you do a vector cross a vector first and then dot the third vector. So the geometric properties, on the other hand, are really like interesting to try to talk about, but some of it is going to be done in the textbook. The first one is that when you take the cross product u cross v, you always get a vector that is orthogonal. That means perpendicular. So u cross v is perpendicular to both u and v. It's actually exercise 63 in the homework that you're going to do. The next one, we will refer to the textbook if you're interested in seeing the proof, is that the magnitude of u cross v is the magnitude of u times the magnitude of the v times sine theta. So it has a look like the dot product. The dot product is times cosine theta. The cross product is times sine theta. Remember that since the cross product is a vector, it's not actually the cross product that's equal to that, it's the magnitude of the cross product. This is going to be useful in a few minutes in different situations. Now u cross v equals 0 if and only if u and v are scalar multiples of each other. So if we have two vectors that are parallel, u cross v is going to be equal to 0. You can also try using the definition, the algebraic definition from the previous page, and you will see why that is. It just things just cancel out pretty quickly. Finally, u cross v is equal to the area of the parallelogram having u and v as adjacent sides. You can see that by going back to property number 2. Magnitude of u is actually the base of a parallelogram, and then magnitude of v times sine theta is going to represent the height of the parallelogram. So if we do base times height, we get the area of the parallelogram. Property 4, when we look backwards, also explains why u cross v equals 0 if and only if u and v are parallel. Indeed, if u and v are parallel, then the parallelogram, well, doesn't exist. It doesn't have it's an area of 0. It's flat. And vice versa. The only way you could have a parallelogram with area 0 is if the two vectors are parallel. We will agree that if one vector is 0 itself, that's parallel to everything. So example here, if we want to find a unit vector that is orthogonal to both u and v, again this will work in 3 dimensions, but you could not find a vector that's perpendicular to u and v if you're in the plane. What we will do is u cross v, and it yields immediately this vector here. Now we want to find a unit vector, so this is not actually good enough. The final answer, let's call it w, would be the answer we found, so -3 to 11, and we have to divide by the magnitude of u cross v. So I'm not going to do everything because it's not very practical to write here, but the magnitude is square root of 121 plus 4 plus 9, so 134. So we have probably forgotten that here. To finish the exercise, the correct answer is the vector -3 to 11 over root 134. And that gives us a unit vector, which is also perpendicular to u and v. So to find the area of a parallelogram that has two edges defined by vectors u and v, super quick, we take the cross product and we see what we get. So u cross v, we apply the algebraic definition, we get -13, -6, 5, again using these determinants. And again, I recommend writing 2, 1, 4 and 1, 3, -1, one over above the other. It makes it easier to see the determinants. And then we take the magnitude of that. So apparently the parallelogram defined by U and V has an area of root 230. So in physics, the torque, or more often than not, it's called the moment of force nowadays, is defined, or is defined as is written here. It's the magnitude of the cross product of two vectors. What two vectors? The first one is the distance between the axis that we are rotating about to where we are applying a force, and the force itself. So what is the torque? It's the tendency for a force to rotate an object about an axis. You can think of opening a door. Its hinges are against the wall, and when you apply a force to the door will more or less willingly open. It depends on how hard you push, but it also depends on how far you are from the hinges. Of course, if you're pushing almost where the hinges are, if you're pushing here, it's a lot harder for this door to turn around. But if you push far away, again, it's going to be easier. So this is where, for those of you who took AP Physics 1 last year, you may remember that you typically, instead of calculating the cross product and then the magnitude, you just calculated the magnitude of the first vector PQ times the magnitude of the second vector, which is F in this example, and then times sine theta. So that's fine, you can do that as well. It's actually quite a bit faster, but it's interesting to know that this is where it came from. So magnitude of PQ times magnitude of F times sine theta. So times the angle between the two vectors. Notice that the angle, we would have to put F near here to see what the angle between F and PQ is. So for example, if we're trying to push this lever down, but we somehow push vertically, which is not ideal. I think we can have an intuition that it would be much more efficient to try to push the lever this way. This is where the sine theta comes into play. If we try to move the lever by pushing directly downward, what is going to be the moment of that force? Let's read the question. A vertical force of 100 newtons is applied at the end of a 50 centimeter lever that is attached to an axle at point P. Find the moment of this force about the point P. So we have to write what the vectors are. F is 100 Newton vertically, so it's going to be the force 0, 0, and -100 because we're going down. PQ is the vector going from P to Q here where the force is applied, and X, as you can see, X is goes this way, so the component in X of PQ is 0, and then if we want to be careful and write answers in newtons and meters or joules, then it's 0.5 times cosine 60, and then the Z component is 0.5 times sine 60. So cross product of these two vectors yields -5,000 cosine 60. Wait, I think that's 50 cosine 60. 0, 0, and then that becomes -25, 0, 0. So what's the magnitude of that? It's of course 25. The units, I didn't talk about it in details, it's newtons times meters, which is joules. Last application here is the triple scalar product. So when you do U dot V cross W, you get the volume of a kind of tilted box like that. It's interesting to see why that works. And let's think about V cross W. We saw that V cross W is a vector that will be perpendicular to V and perpendicular to W. So let's say V cross W goes up like that, it's perpendicular to V, it's perpendicular to W. We know the magnitude of V cross W is actually the area of the parallelogram, so it's the area of the base. So then when we do U dot this, it's going to actually happen to be, if you think of the dot product, it's going to be the magnitude of U times cosine between these two angles times the magnitude of V cross W. U cosine the angle yields the projection of U onto V cross W. So this vector here is, or this length here, from here to there, is magnitude of U cosine the angle. And then if we multiply that with the magnitude of V cross W, we saw that this is equal to the base. The projection is equal to the height, so we have base times height, and that yields the volume of the parallelepiped. It may happen if depending on the orientations of the vectors, that you actually get a negative number at this point, because V cross W, if V was defined here and W there, V cross W would actually point downwards. So be careful. That's a little detail, but we need to take the absolute value of the result, because volumes are always positive. So, very quick example. If we define a parallelepiped by three edges U, V, and W, what is generated by these three vectors, we just apply U dot V cross W, which is U is 214, V cross W, after using the algebraic definition, is -9, -1, -12, and the final result is 67 when we use absolute values. So let's put the absolute values right there. So the volume is 67. Thank you very much.